Okay, we start up. You're done with the first report exercise. I hope everybody is happy. Or I haven't had the time to look at it yet. Too many of them. I have to find a dice and then give you some grades. You will get the grade from 0 to 100 on that exercise and all these following report exercises. So if you want to argue about it afterwards, be my guest. Any questions before we begin? So you have been given now a new exercise, and I put the deadline to be Sunday. I mean, you got this one a little late. So I'm going also to go through a little bit, say, some concepts behind this exercise. This is also then going to be sort of a pre-study for the next report exercise. So you should spend some time on this one. So you are to create a simple form for a laminar case. That can actually be a good idea to have it lying on your hard drive sort of as a setup for a laminar steady state case. Remember, the only laminar solver we had used so far, and that has been icofoam, but that's a transient solver. Can be nice to have a steady state solver as well. And yes, you can take any of these turbulent setups and sort of change them to a laminar case. No problem. And yes, this is your problem. Flow between two parallel plates, laminar, steady state. And yes, you should then send in a fully developed flow. Actually, you don't have to. Here I said you should have a Reynolds number of 10. That's fairly low. It's so low that if this length equals the height h, then actually if you send in a flat profile, it's going to be fully developed at the outlet. So it only takes 1h, you might say, in the streamwise direction before the flow is fully developed with such a low Reynolds number. But I think it's a good idea to, give you a challenge here. Send in a fully developed flow, and then we are going to create some really, really stupid meshes and then see what happens. And you know, you don't need many cells, so it should be very cheap simulations. And first thing, yes, we are going to merge some cell blocks. That's actually an option you should be aware of. And also, well, we talked about the edges already, so here you can play around with it. So we are going to construct a really, really stupid mesh. And then it's your job to sort of tune the setup so you don't see the mesh in the solution, because we know the analytical solution when it's fully developed. So that is going to be your job. And yes, we are going to look at snappy hex mesh, and that is a big topic. So I'll try to show you something about this today. I had at least planned. Okay. The deadline is set to be Sunday late. Is that okay? No problem with that one. I mean, you don't get any scores for these exercises anyway, but I mean, they are important as a pre-study for the next report exercise. So yeah, you should fight with it. Okay? Now then, let's have a look. Here, I think I have created a case for you. I think I called it channel. Let's see, CD channel. So we start with this one. And for this channel case, it's just sort of the basics already. But let's have a look at it. For the mesh system, and we have it here. I'll put this one out for you later so you can have it and play around with. So I have a bunch of vertices here, 8, and then I have 8 more, and then I have 2 blocks. And yes, I've done it very, very easy here. Now let's do it very, very easy initially here, like that. Each block is now 5 by 5 cells in the X and Y direction, no grading, no nothing. So 2 blocks next to each other. And you can see here now, for the boundary, I have commented out almost everything, except something down here. So this is actually possible when you're playing with a mesh. You don't have to specify inlet, outlet, borders, front and back. You can just do it rather crudely, and then just have a look at the mesh. You don't even need the 0 folder. You don't even need the constant folder. You only need the system folder with block mesh dict and a control dict. So you can do it initially very, very, say, simplified down. But I'm going to use this last part here. Merge, patch, pairs. That one I am going to have a look at. So let's try this one. Let's see now. We have a block mesh. Mesh, thank you. Something like that. And the bounding box from 0, 0 to 2 and 1. So it's 2 by 1. And I don't have many cells, no problem there. So fairly easy. And I mean, we can always run a check mesh just to see that we have the mesh is okay. And then we can have a look at it. Parafoam. Let's see now. So here we have the mesh, and there you see what has happened. I have one block 5 by 5, and then I have another block 5 by 10 or something, and then they have merged. They have sort of been glued together. Rather messy, if you ask me. So we don't have hexa cells here anymore. We have something very, very strange indeed. But this is actually quite possible. And it can be convenient when you have one block with a totally different cell spacing, meshing, stretching, whatever, and you want to glue that one into another block. This is actually an option. But it comes with a price, as you can see. The mesh there is quite distorted, to say the very least. So not so good. If we now go back to this block mesh dict, and here I changed it now to 5 by 5. And if I just save this and then run block mesh again, block mesh, thank you. And then we had parafoam. So now it's not going to be any noticeable change one block to the next. I have exactly the same mesh. If this is the case, then of course you don't have to merge them. Actually, you don't have to do anything. So no problem here. But if the second block is sort of different from the first one, then you have to do something special. Then you can merge them. Okay. Let's see how this is done. If you look at the corners here, and if you think of the problem, 2 equal blocks next to each other, then actually I have used 8 plus 8 corners. That shouldn't be necessary, should it? Let's have a look. So this is what you would normally do when you have two neighbor blocks and they are equal in size. Something like this. Let's see now. There and there and there and there. Okay. How would you number these corners? Normally, you would do then the following. If you do it systematically, say 0, 1, 2, 3, 4, 5, and then we have a corner up here, 6, and the last one, 7. That should be the first block. And then you only need these 4 additional corners, meaning this 1, 2, 6, 5 plate. That face is going to sort of be an interface between the two blocks. So they don't need their own corners to say, just to do it simple. So here I could have continued now with 8, 9, 10, 11 or something like that. But if you're going to merge them, you can't do it like that. You have to specify the second block with its own corners. So here I have to sort of use the same location here, but I have to call it something else. So here I was, let's see now, 7. So now I used 8, 9, 10, and also up here 11, and this one then should be 12, 13, 14, and the last one here 15. So I use the same location, but they have sort of 2 names. Sadly, that is the price. Of course, if they don't match, then definitely you have to do it like that. For instance, when we had the exercise with the backward facing step, typically what we did there was one initial block over the step, and then we had one long block here, and then we had another block down here. So we used 3 blocks. What we could have done was something like this. We just have 2 blocks, and then we make a merge here for these 2 blocks. That would actually be possible. So the first block then definitely needs these corners here, but the second block, he will then use these corners like that. Of course, then this face doesn't match, but that doesn't matter. So yeah, you could have sort of specified a wall here, a solid wall, but when we merge these two, then this wall is going to be destroyed, going to be internal cells when you merge these 2 blocks. So yeah, that would be an option. Not that it's saved us much work, but just wanted to show you as a possibility. So merging, that means you need 2 separate blocks, and they need their own, say, corners. Even though maybe several of these corner points are the same in both blocks. Okay, any questions to that one? That's okay. So there you see my two blocks, 1 to 7 and then 8 to 15. Although 4 of these corners will actually have the same location. But we have to do it like this anyway. And now I have the same number of cells. Let's change this one then to something else. Say I have 5 cells in the y direction to the left block. Let's do something that definitely doesn't match. Let's say 12. Why not? So now I have 12 cells. So 12 and 5 cells are then going to be merged. And I skip everything here, inlet, outlet, whatever. And the way to do this, you have to define what's called a master and a slave. They don't have to be named master and slave. They could be named anything, left, right, or whatever you want. But the order here, the first one is the master. He's in charge. He's going to stay. While this one is going to be adjusted, the slave. So for the master, then my patch will be the right face in the first block, and the slave, the left face in the second block, and then glue them together. And that's merge patch pairs. That's his job. And that's it. So let's have a look at this one. We save it, and then create the mesh. Block mesh, and I don't even bother to check it. Parafoam. So here then you see what he's doing. So nobody has said that for a cell you need 4 faces. In open form, yes, you can have what's called poly mesh. You can have n number of faces. N can be a big number actually. So several of these blocks here will actually be quite strange. And this one, oh, that's a nasty one, isn't it? Squeezed almost to 0 area. We don't like that. But we have no choice. And if you look at the wireframe in 3D, then you'll see they don't really align up all that well. So this is rather a messy mesh, I would say. Still, it should work. We didn't have any problems, did we? Let's do the check mesh. Oh, he's okay, no problem. So he has some values for skewness, orthogonality, and so on and so forth. But he still claims the mesh is okay. And if you look at the mesh types, actually he has been able to create everybody as hexa. A little bit weird. I thought some of them would be polyhedra. Well, actually, yes, we have 9 of them. So there you see the price you pay. You get not hexa, but poly in some cells. The hexa is always preferable to say have a nice coefficient matrix, efficiently numerical solvers. But sometimes we really don't have an option, so we have to deal with that one. Okay, that was the merging. Any questions to that one? Now let's try to run this case. Let's see what kind of case we have here. We can have a look at control dict. Let's see now. I think I stole the setup from the Pitts Daily case actually. We have a function here, streamlines. I don't want that one. Get rid of that one. Delete. And else, no, it should be okay. it's steady state, simple form. Start from 0 and we have maximum 2000. Okay, good enough. Then what about our other files? Let's see now. We have in the constant folder, I have an FV option. I don't want the FV options. Can't we delete it here? No, we can't. Well, we delete it in this one then. ls constant. And then I remove constant FV options. Done. So now the constant folder should be, of course, with the polymesh folder. And then we have transport properties and I have turbulence properties, at least on my version here. Transport model Newtonian. Let's change that one. Viscosity 0.1. Something like that. And then I change turbulence properties. Yes, clearly this is a case for stolen from the Pitts Daily setup. You see they have tried it with several turbulence models. Now I want a laminar case. So I can actually do the following. Laminar. And then I don't need anything of this. I can just delete it. Done. Do it crudely. Simple. It should work. At least on my version. Let's see what else we have here. We have the 0 folder. Oh, here we have a whole bunch of files. But now I want a laminar case. The only files I need here is the velocity and the pressure. Okay, let's clear up this one. Let's clear up that one. ls, the 0 folder, a whole bunch of files. Remove 0, cell to region, whatever that might be. Epsilon I don't want. K I don't want. Nu tilde, well, I don't want any of them. Omega, and finally y plus. So now I have only 2 files in my 0 folder. Okay, let's have a look at those then. 0, and let's start with the velocity here. This was not from the Pitts Daily case. Inlet is cyclic, outlet is cyclic. I don't want that. Let's change it. Inlet, I want that one to be fixed. Value, thank you. And then value, well, we do it crudely here, uniform. And it's velocity, so we need 3 numbers here. That's the inlet, outlet, 0 gradient. 0 gradient. Top and bottom, what did we call them here in BlockMeshDict? Let's have a look. Did I have top and bottom? Yes, I have top and bottom. Both were type wall. Okay, we can do it like that. Top, type no slip, and the bottom type no slip. Front and back type empty. There we have it. What about the P file? I have to change that one as well, I guess. Yeah. Inlet, I choose 0 gradient. And the outlet should be fixed. Why is this? I mean, I'm sending in a constant velocity. Should be possible then to specify at the inlet a constant pressure, and then the outlet should then be zero gradient for both velocity and the pressure. It's actually an option, it's possible, but the numerics, the way they have built OpenFOAM, he doesn't like it. He likes it much better when you're sending in a known velocity, keep then the pressure at the inlet as zero gradient, and then you use fixed value at the outlet. So he likes that much better. Let's see now, value uniform 0. Why not? Top should then be zero gradient, and the bottom zero gradient. There we have it. Something like that. Then we should be good to go. But before we run, let's have a look at some of these other files here in our system folder. We have the schemes. And here you see we have a whole bunch of schemes. Of course, the time derivative, steady state. No choice there. And the gradient, linear, that's okay. And then this is sort of the crucial one normally. That's the non-linear terms in the Navier-Stokes. So here we have something crazy, bounded Gauss linear upwind, whatever that might be. Let's do it easy. Gauss always starts with Gauss, and then we choose just the linear. That should be a central differencing scheme, second order. Unstable, jumpy, but should be the best accuracy if you can make it stable. And then we have some turbulence things. Actually, I don't need any of these. You shouldn't mess around with those at all. Now, it doesn't matter if they are present here. I mean, he's not going to use them anyway, but you could actually delete them. But for now, let's just leave it. Should be okay. So I'll say about that one. And then finally, solution. So I have the pressure using a multigrid method. Looks okay. And then I have a whole bunch of equations here using a smooth solver. And here I could actually do it quite crudely. I don't want him to solve all these equations. I only need you. So yes, that's actually quite possible. And then for the simple algorithm, we have, let's see now, non-orthogonal correctors set to be 0. Maybe a bad idea here, but that's your job. Consistent, yes, I will always recommend yes here. This is a much more efficient, simple version. It's called Simple C, actually. And that one also allows you to keep quite high relaxation factors. If you say no here, then you have to go down to, for the pressure, maybe 0.34, for the velocity, 0.7. It will take much longer time to find a solution. So always yes. Then I have the pressure and the velocity components. And here also all these turbulent things, which I don't want. So let's get rid of them. Well, here these levels were fairly high. So let's change it. 10 to the power of -5 should be okay, I think. Something like that. And then you have these two guys. What is this? That is a reference pressure. And yes, you need it some cases. If you don't specify the pressure anywhere along your boundary, then these has to be present. If you forget them, OpenFOAM will yell at you. I don't want to solve this. I can't solve it. I need a reference pressure somewhere. So now we have a reference pressure already. We have specified it at the outlet. Hence, I don't need those two. So let's just delete them. And then we use 0.9 for U, and for everything else, actually we could just have set P here, because that's the only thing else I have. So here you see sort of now a sort of simplified version of simple foam to be a laminar case. Let's see now, we have to go back here into our block mesh, because actually I have commented out everything here, inlet, outlet, and so on and so forth. So let's try to uncomment this one, there and there. So now, let's see if we can make it run. Save. Let's see now, I have to create the mesh again. Block, mesh. Yeah, no problems here. Yeah, should be okay. And for the different patches, inlet, outlet, top, bottom, front and back. Yeah, it looks okay. Then let's just do the check mesh. No, it's okay. I mean here, when you have specified the different patches, inlet, outlet, top, bottom, whatever, if you have a whole bunch of different zero files, which you don't need, actually you have to go into all of them and specify the correct boundary conditions, even though they are not going to be used. So that's a little bit messy. Much easier here for me to just destroy them, because I don't need them for the K, epsilon, and all these turbulent quantities. Let's try to run it. Simple foam. Well, that went fast. 51 iterations converged. My residuals are really low. Looks beautiful. Okay, let's have a look at the solution. Para foam. Let's see now. Apply. And then we have the latest one here. So this is the pressure. Does it make sense? Well, not so easy to see with these colors here. You're going to get high pressure in the corners, because you have to sort of force the flat velocity profile into the center. And when it's fully developed, your pressure gradient should be constant. That's fully developed flow for you. And actually, it looks quite okay. You can't really see the details here. And if you look at the mesh on top of this solution, we know there are some fishy things going on in this region here, but you can't really tell, can you? Because this is sort of a warning. If you see the mesh in your solution, then that's not good. You shouldn't see the mesh. And we have some shadows here, not so easy to see actually. What about the velocity? A little bit more revealing. Oh yes, something clearly is happening here in this merge zone. That is not good. Here you can clearly see the mesh. If you do it like that. Not good, not good. Okay. Now, instead of just using sort of the default setup here for velocity and pressure, let's just keep the mesh as a wireframe. We can even go to 2D. Clearly it's not the best mesh. And now I want to have a contour plot, a little bit more detailed than just this color thing. And yeah, that's actually possible. You have a contour here. Or you can go inside filters and search for it, contours. So if you click on that one, then you see my only option here is pressure. I can only plot the pressure. Well, okay, fair enough. And if you just click on apply, the default, Well, actually, he creates one single pressure contour, and here you can't even see it. If we remove the background, no, you can't really see it. So the default here is quite terrible. So let's get rid of that one. Instead, let's create a range from 0 to the maximum pressure and the number of samples. Let's choose 40. Something like that. Now I have a whole bunch of different contours, and well, we got it only in, or at least visible, here in this center region, and really looks messy, doesn't it? Very messy indeed. Couldn't we get that one a little bit better? Let's see now. The pressure. What was the range of the pressure actually? Let's have a look. The pressure should go from 0 to 3. Yeah, should be something like that. Okay. From 0 to 3. Let's see if we can make this one better. The contour plot. Get rid of that one. And then create a new range. From 0 to 3. Now he says he has everything here. Okay, let's create some more then. What about 100? We still only get it in this center region. A little bit weird, but never mind. My point is, yes, you can go back to 30, whatever. You can get it a little bit more detailed, especially where the mesh is sort of distorted. Now I want to have the velocity. I want to have contour plot of the velocity. But that's actually not an option. The only thing he has here is scalar, and I only have the pressure. Okay, then what do we do? Delete that one. And now we have to create a scalar field for the velocity. Remember, the velocity is a vector. How can we create a scalar field? Well, you have some filters, and we have something called a calculator. That's a good one. Here you can actually create a lot of different stuff if you want. Play around with your variables and create whatever you want. Result array name first is called result. That was a bad name. You have to give him a name, not result. What should we call him? Reidar, that's a good name. Have to call him something. And now here comes your expression, your calculation. What I want is the velocity magnitude. How can I get that one? I'm going to need a square root. Should be here somewhere. Square root, parenthesis, and then I'm going to insert what? Ux, and I want that one squared, plus, and then Uy squared. Something like that. And apply. Yeah, we didn't get any errors. And I mean, this is actually then the same plot as we would have gotten sort of by the default. That's not what I want. I want this one a little bit more detailed. So get rid of that one. We can have this one displayed. in a 2D case. Should be possible. And then we add another contour. Now I should have the option of not only the pressure, but I can contour the other one as well. Beautiful. And he suggests only one contour line. That's stupid. I want many. How many do we want? 40. Generate and then apply. Clearly, yes, something really messy is going on here in this center region. Not good at all. I don't really get why he only plots it in the center. I want them all over the place, actually. Yeah, I can have a look at that one in the break. Should be here somewhere. We have a lot of options here, so yeah, you can do a lot with these contour plots. But I think they are going to reveal more about the problems with, say, dirty meshes than just the default color plots. Of course, you have another option. You can save all your data. You can create these C files for the position of the different cell centers, transfer everything into MATLAB, and use contour plot there. That's actually possible. But I think these contour lines, they should actually work. I'll have a look at it in the break so that we can get them all over the place. Any questions? Okay, let's take a break.